Okay, correlation. So correlation simply means correlation. Co could imply you have two things and we are trying to relate two things. So what does statistical correlation mean? Statistical correlation simply studies the relationship between two random variables. So let's have two variables. And the variables are random. Correlation is simply the relationship between the two variables, x and y. So y is what we call the response or dependent variable. And x is the predictor or independent variable. So we are going to make use of x to predict something about y. Let's say y and x are related to each other. They are related to each other through some underlying behavior. So I can say y is related to x through some underlying relationship. And in mathematics, that underlying relationship is typically defined by a function. So I'll call that function f. And in short notation, I could write y is equal to f of x. Y is related to x through f. So f is going to define the type of the relationship that exists between x and y. So in statistics, the goal is to identify the relationship f that exists between x and y using observed data. So if I consistently observe data for both x and y, then somehow I'll know how x is affecting y. Since x and y are related to each other, when we collect data, they should always be measured simultaneously. In other words, the data is paired. Anytime I collect a value of x, I'd also collect a value of y. As an example, I could have GPA versus the time spent at the library. So GPA of a student will depend on, or may depend on, the time spent by a student at the library. Now, what type of relationship exists between Y and X, we do not know. But if I observed 15 students over time and recorded their GPA and the amount of time they spent at the library, then I can sort of come up with a model or an equation that would describe the relationship between Y and X. So regression analysis is used to quantify the relationship that exists between X and Y. What do we mean by quantifying? We're trying to put it in terms of mathematical terms. We are going to explain the relationship that exists between Y and X using an equation. And that equation is what we call a model. Now, if that equation that we are trying to use to describe the relationship, if it is linear, then the regression is called linear regression. And if the relationship is nonlinear, then it is nonlinear regression. So depending on the type of relationship we see visually, we would either go for a linear regression analysis or a nonlinear regression analysis. So how do we identify the regression analysis that is appropriate to describe the relationship between Y and X? Well, we have to simply get a scatter diagram. A scatter diagram would simply be diagrams of this sort. Here, what we call as the explanatory variable is simply the predictor that I spoke about, predictor or independent variable. So a scatter diagram simply plots the points on a plane, and you can see, I sort of see a pattern just by looking at the data. So the first set of points here, the pattern that my eye captures will simply be a line that is going up. So I can look at that data and immediately say, well, I would use linear regression. And the second one, the line sort of going down, that is the pattern that I see. So again, I would conclude linear regression. The next case, it doesn't look like a line, rather it looks like a curve. It's going up, then down, and clearly that is not linear, so we must use nonlinear regression. The same in the next case, we don't have a strictly linear relationship. The underlying pattern is of that sort. Since it is not a line, rather a curve of some sort, that is nonlinear. The last one is an interesting case. There is no reasonable pattern that I can see or that I can quantify mathematically. For instance, if I want to recognize the pattern, perhaps I would say that is a pattern that I see. There's nothing wrong with that because that's what my eye captures. Someone else might look at it and say, oh, I'd have that and that. That's a pattern that I see. But you've got to keep in mind that those aren't functions. They would fail the vertical line test. So from a statistical standpoint, that particular pattern that we see here is not a meaningful pattern. So pretty much one can conclude that there is no pattern at all, or there is no significant relationship between the X variable and the Y variable. Another way to think about it would be to perhaps say, okay, that's the line that describes the relationship between Y and X. So if that is the case, we have a flat line. So no matter what happens to X, Y remains the same. Y remains unaffected. Y remains unchanged for whatever change that could be in X. So here we would end up saying that there is no relationship between Y and X. So a proper relationship is something where changes in Y should affect, changes in X should affect Y in some form. In the first two graphs, they were linear. The second two, non-linear. The last case, no matter how X changes, Y doesn't change. One other case So at least in the very last one, I was able to draw a horizontal line. But what if the data ended up being something like that? So clearly that indicates no relationship whatsoever. So as X changes, Y is all over the place, and Y and X are not in sync at all. They're just going all over the place. So in that case, we would have no relationship between X and Y. So anytime prior to performing a regression analysis, the first thing one has to do is to take the powered data, the X sample and the Y sample, and put it either in Excel, your calculator, or any statistical software, and get a scatter diagram such as these 5 or 6 plots that we have. Once you get this scatter diagram or a scatter plot, you can determine if there is a relationship. If there is, the next question to ask is it linear or is it non-linear? If it is linear, you go for linear regression. If it is non-linear, we do non-linear regression. If there is no relationship at all, we just stop and give up. By give up, I mean give up on the sample. So in linear regression analysis, that is the underlying relationship between x and y is linear. We get that idea from a scatter diagram, so we proceed with a linear regression analysis. But prior to going for a complete regression analysis, one may want to know how strong the relationship is. So we want to assess the strength of linear regression between the two variables x and y. So So the strength of the linear relationship between x and y can be calculated using the linear correlation coefficient, and it is denoted by the letter little r. So suppose we have 10 observations, x1, x2, x3, all the way up to xn. And since the data has to be paired, for each of those x values, we have corresponding y values. And since we have the sample for x and the sample for y, so I can use all the x samples to get the mean x bar and standard deviation S sub x. In a similar manner, I could use all the y values to get the mean y bar and standard deviation S sub y. Then the formula, it might seem a bit scary, but in reality it is not. This can be done easily using a calculator. The linear correlation coefficient is given by this formula, 1 divided by n minus 1 So it's simply xi minus x bar over sx, yi minus y bar divided by sy. So if you notice, that simply is the z-score of every observation, of each observation in the X sample. And the second part is the z-score of each observation in the Y sample. So what we're doing is we're pretty much finding z-scores for the X sample, z-scores for the Y sample. We are multiplying them together. So that is the multiplication, and we are summing them all. So we take I equals 1 through 10 simply means we're going to, and the sideways m is simply sum. So we're going to find the z-score of every single observation in the X sample, z-score of every single observation in the Y sample, multiply them together, we will get 10 z-score products, and we sum them all and we divide it by n minus 1. In our example, that would be 9. So when we do that, we would get R, which is simply the linear correlation coefficient. So one thing to note about R is that the value of R the value of R has to be, or will always be, between -1 and 1. So if it falls anywhere above 0.8, typically we would say a strong correlation. But in practice, we expect it to be closer to closer to 1, such as 0.9 or 0.95, etc. So typically 0.8 and above means something. In other words, there is a meaningful relationship between X and Y. So that is strong positive correlation. If the value of R is between -1 and -8, that is a strong negative correlation. In other words, as X increases, Y goes in the other direction, Y decreases. Strong positive would mean as X increases, Y also increases. If we are between 0.5 and 0.8, we can say moderately negative. And over there, moderately positive. If it falls between 0 and 0.5, or between negative 0.5 and 0, we simply end up saying oops. Weakly negative and weakly positive relationship. So I left out the middle part right here. If it is exactly 0, then there is no correlation at all. That would go back to the scatter diagram that I showed earlier, the last one, where there is no relationship between X and Y at all. And if we try to come up with a value of R, that value would be close to 0. So here are some scatter diagrams between two variables, X and Y. And in the first one, I can draw a perfect straight line between X and or through all the data points. So if I compute the value of R is going to be exactly 1. And since as X increases, Y is also increasing, the relationship here is strong, positive. And the next one, we sort of have a relationship between X and Y, but it is not perfect in the sense Y has some variability. So there are some values above the line, below the line, but there is a relationship between X and Y. So here, R is going to be between 0 and 1, but this would be strongly positive. The next case, it's weird looking. I can draw a line, but it is not going to explain the relationship in a proper way, the relationship between X and Y. So here, the value of R would be between 0 and 1, technically 0 and 0.5 perhaps, but this is a weak positive relationship. The next case, as X increases, Y decreases in a perfect way. So this would be an example of a negative correlation. And the value of R is going to be exactly equal to -1 because it is a perfectly negative correlation. When I say strong, I should say strongest negative correlation. The next one, I have a relationship of that sort. Well, it is going to be between 0 and 1, the value of R. Would I call it the strongest negative correlation? No, because there is some variation. It is not as perfect as the previous plot. So this would have a negative correlation, but it is not the strongest. I could say strong negative correlation. In the next case, if I drew a line, that line is not going to explain the data that we see. We don't have a perfectly linear relationship. So the value of R would be between 0 and -1, or -1 and 0, but it'll be closer to 0 than it is to -1. So this would be weak negative correlation. In the next case, R would be approximately equal to 0, because as X changes, Y is all over the place. That scatter diagram is similar to the one that I drew earlier. So R is approximately equal to 0, and there is no correlation between X and Y. So the last one, we have to be cautious. The value of R in this problem could be, for that graph, for the data in that graph, it's going to lie between -1 and 1. Based on experience, I'm thinking it is going to be more on the negative side. But the danger here is R is not useful. Even though I am going to get a number between -1 and 1, the value of R that we get is not useful. It is not meaningful, because the relationship that we have is not linear at all. This is a non-linear relationship. So the value of R is only useful if the relationship between X and Y is linear. If it is non-linear, I can come up with a value for R, but it is meaningless. So here is an example where we want to match the 4 correlation values with the plots here. The values that are given to us are A, -0.969, B, -0.049, C, -1, and D, -0.992. So let's start with the first one. The first one has a perfect linear relationship. In other words, I can connect the dots. It would form a perfect line, or it will form a perfect line. There are no observations above or below the dots. There are no dots above or below the line, so it is perfectly linear. And as X increases, Y decreases. So the value of R must be -1. So that corresponds to C. Let's go to the plots below, and then we can address the other two. So if you look at the third plot, it is decreasing, or there is a negative correlation. But is it perfect though? Is it reasonable compared to number 2 and number 4? At least those two look like a line. They're not as perfect, but they at least look like a line. Here, if I drew a line, there are too many dots above the line, too many below the line. In other words, the observations vary too much, and the line cannot do a good job in explaining the dots. So that must have the lowest R value possible, and it must be negative. So of the remaining choices, A, B, and D, B is very close to 0. So it is more likely that plot 3 has a value of negative 0.049 for linear correlation coefficient. Now, 2 and 4, by direct comparison, we can say that the line in plot 2 describes the dots or the observations well. In the sense, you can look at the dots. The dots aren't too far away from the line. They are pretty close to the line. But if you look at plot 4, there are too many observations that are far away from the line compared to plot 2. So both plot 2 as well as 4, both of them have a negative correlation, but 2 is stronger than 4 because most of the observations, not all of them, most of the observations lie really, really close to the line that we drew. So plot 2 has to have a stronger negative correlation coefficient. In other words, it has to be close to -1 compared to plot 4. So the two values that we have left are negative 0.969 and negative 0.992. And the closer one, the value that is closer to -1 is negative 0.992. So that would be the correlation coefficient for 2. And for the last one, the correlation coefficient would be negative 0.969. So here we have a data set where the Gallup organization surveyed Americans regarding their commute time to work. And they did a survey, and according to the Gallup organization, they have this Gallup Healthways well-being index score. And how do they come up with that score? They consider various factors: life evaluation, their emotional health, their physical health, healthy behavior, work environment, and basic access. You can find the data at that link. So what we're trying to do is we're trying to see if there is a relationship between the commute time and the Gallup Healthways Wellbeing Index Composite Score. I'll just call it the G score because it's just lengthy. So we want to know if there is a connection between the commute time and the well-being index score, which is simply the G score that I listed here. So if you have a lower commute time, does it mean you're really, really healthy? And if you take longer to go to work, then that you're not healthy. So that's the purpose of this study. Part A wants to know, which variable do you believe is likely the explanatory variable and which is the response? Now, the well-being score can be described in terms of commute time. Or the commute time can be defined in terms of the well-being score. So which would depend on which? So that is the key question to answer. So the explanatory variable would simply be the x variable, and the response variable would be the y variable. So here, x is the independent variable, y is the dependent variable. So how healthy you are, or how great you are based on Gallup's scoring process, is going to depend on the commute time and not the other way around. So the G score here would be y, and that would be x. And we want to determine if there is a relationship between the two. So first, we want to draw a scatter diagram. So we can do this using your calculator. I'm going to put all the x values the commute time in the first list and the y values in the second list. We can go to start plot, turn it on, and of all the options, the first one that we have is the scatter plot. So I'm just going to leave it as is. And it asks us x list and y list. We had all the x values in list 1, y values in list 2. So we can leave it as is, and we will hit graph. We don't see anything because we have to adjust the scale for the x values. The x values range from 5 to 105. So I'm going to change the minimum and the maximum from 0 to 110. The y values hover in the 60s. So perhaps I would start at 60 and go all the way up to 72. And that's the relationship that we see between x and y. And you can see that the longer the commute time, the less healthy you end up being. In other words, it seems to decrease. So the relationship that you see from the scatter plot is negative and it's linear. We would like to find the mean and the standard deviation. for each of those lists. For the y variable, the mean is 66.93. The standard deviation is 1.709. For the x variable, which is the commute time, the x bar is 43.86, and standard deviation is 34.98. So we have the means for x and y. We have the standard deviation for x and y. Now I'm going to use the formula that I have for linear correlation coefficient over here and try to find the value of R, but using which I'll determine if there is a strong correlation or not. I know the correlation is negative, but I want to know if it is strong or not. Just by looking at the graph, I can say that there is a strong negative correlation. So my guess is that the value of R is going to be close to -1. Let's see if it is close to -1. So note the formula is 1 over n minus 1. We have 7 observations. So our formula would reduce to 1 over 6. You sum all 7 observations and that part is done using the calculator. So how do we go about doing this easily in the calculator? The first step is to compute xi minus x bar divided by sx. I know all of the x values are in list 1, so I'm going to do second 1 minus the mean of the x values is 43.86. Divide by the standard deviation of the x values, which is 34.98. Multiply. So that is going to create the z-scores for all the x values. Now I'm going to multiply that by all the y values, which are in list 2, minus the mean of the y values, divide that by the standard deviation. So this is going to give us a list of values corresponding to that evaluation. So first part right there is L1 minus 43.86 over 34.98. L2 minus 66.93 divided by 1.709. You multiply, and I'm going to store it using the store key to list 3. Did I make a mistake? Let's see. So now the values are stored in list 3. So if you go back to our table, list 3 has all possible values, the 7 values, which are simply the product of the X z-scores and Y z-scores. I have to sum these values now. So to sum all the values, press second start, over to math, select option number 5, you get sum. I want to sum everything in list 3. That gives me negative 5.886. We want to divide that by n minus 1. N minus 1 in our case is 6. So I divide by 6. I end up getting the value of r to be negative 0.9810. As I mentioned at the very beginning of this problem, I expected this to be strongly negative in terms of correlation. And you can see that the value of r is close to negative 1, and it is negative 0.981.